Now, as you know, the purpose of this paper is to extend the concept of regression to the case when you have discrete data. So thus far, we have really been considering several cases. For example, we have considered why count data or binary data situations may arise and why it might be relevant to build a regression model for this data. We have seen the motivation in terms of something called binary choice. We have written out the very popular logistic regression model and worked out the maximum likelihood equations for this. We have also done this in case we have a probit link for binary data. We have also done this for the case where we have a count outcome. Now, as you can see, the forms of the regression equations are very similar, and this suggests that they might all be special cases of some general score equation which can be derived for the class of generalized linear models. So this is the class of score equations which we are going to develop in this module. We will see that the equations do not have explicit solutions. We will briefly mention some numerical methods for solving the equations, and in the next module we will go into details for these equations. The learning objectives for this module are: first, we will define the various components of the one-parameter exponential family. Second, we shall write out the likelihood for this family and define the score function. Third, we will find a general form for the information matrix. And finally, we shall see how the score function and the information matrix will simplify for the case where we have something called a canonical link. So the one-parameter exponential family. The general form of this, as you know, is given by f of y theta equal to exponential of y theta minus some function b of theta divided by a function a of phi plus c of y and phi. Now, theta here is a parameter which is called the canonical parameter, and phi is a scale parameter which is optional in the sense that it may or may not be present. Now, we all know that the Bernoulli family of distributions is a particular case of the one-parameter exponential family. Now, as you know, the natural parameter for this family is pi, which is the probability of a success. However, if you were to write out the likelihood for this family in the form in which I have written it here, you will see that the coefficient of y turns out not to be pi, but a function of it log of pi over 1 minus pi, which you know by now to be the logit of pi. So this is the concept of a canonical parameter, that is, that although we could have parametrized the family in terms of a parameter which is more natural, like the probability of success for the Bernoulli distributions, when we write it in this particular mathematical form, we may as well use another parameter to index this family, which is the coefficient of y, and it is this coefficient which is called the canonical parameter. In fact, the form in which I have written the one-parameter exponential family is a particular form which has many variants, and this is called the canonical form. Now, phi, as I said, is an optional scale parameter. As you know, when we write out the Bernoulli family of distributions, there is only one parameter, which is pi or logit of pi, and hence we can say that the Bernoulli family is a one-parameter exponential family with no scale parameter. Similarly, if we were to write out the Poisson distribution, you will see that in this case the canonical parameter turns out to be log of lambda, where lambda is the rate, and also in this case the log likelihood can be written entirely in terms of log lambda. So for the Poisson family also, it turns out that there is no scale parameter. For the normal family, however, you will see that theta turns out to be nu, the normal mean, And this is one family in which there is a scale parameter, which is the usual normal variance sigma square turns out to be A of phi. The gamma family is also a particular case of the one parameter exponential family, and here you will see that there are two parameters, one being the canonical parameter and one the scale parameter. However, our task does not end here, because our purpose is not to simply write out the likelihood of y, but to relate it to a set of covariates. To this end, I assume that we have also observed data on a p vector of covariates, which I shall denote by x, and I define something called a linear predictor, which I denote by eta, and which is in fact classically denoted by eta in textbooks, which I set equal to x prime of beta, beta being my unknown vector of regression coefficients. I thus have two components which are often referred to in the literature as the random component. Y is random because it has a probability distribution as specified on this slide. And eta is the fixed component because it relates to the covariates. My next task must be to relate these two, and I can do this by using a link function, which I shall denote by g, and g of mu is equal to eta. So this is my equation which relates my random component to my fixed component. Mu, of course, is the expectation of y. So let us consider an example. Y follows normal mu sigma squared. Now, as you know, we can write log of f in this case in the form which is given here, that is log of f is equal to minus 1 over 2 sigma squared y minus mu whole squared minus half log of 2 pi sigma squared, which after some manipulation can be written as y mu minus mu square by 2 by sigma square minus y square by 2 sigma square minus half log 2 pi sigma square. Now this is the form in which we have expressed the generalized linear model. The coefficient of y in this case is mu, and thus my canonical parameter for this family is theta equal to mu. So this is one case where my canonical parameter is the same as my natural choice of parameter. The scale parameter is given by sigma square, and in fact A of phi is equal to phi is equal to sigma square. The second and the third terms are absorbed in the function c of y phi. Let us consider another example. So suppose we have data on proportions. I express this by saying that y follows 1 over n into binomial n of pi. N, of course, could be 1, in which case we have data from the Bernoulli family. My likelihood can now be expressed as the familiar binomial likelihood, which turns out to be given by log of f equal to log of n factorial minus log of ny factorial minus log of n into 1 minus y factorial plus ny log pi plus n into 1 minus y log of 1 minus pi. This, after some manipulation, can be written as y into log of pi over 1 minus pi plus log of 1 minus pi divided by 1 over n plus some constant term which does not involve pi. Looking at the coefficient of y, we can say from this slide that the canonical parameter is given by theta equal to log of pi over 1 minus pi. You can also see that the function b theta is given by minus log of 1 minus pi, which of course needs to be expressed as a function of theta, And finally, that the divisor of the first term is 1 over n involving no additional parameters, and thus to repeat, as I have said before, that the binomial family does not contain any scale parameter. We have something called a canonical link. This occurs when eta is equal to theta. Now recall, for the normal family, theta, my canonical parameter, was equal to mu. So this means that if the canonical link were to hold for the normal family, we would have eta equal to mu, which means, in other words, that mu is equal to eta is equal to x prime beta by virtue of the definition of eta, and we have a situation of usual linear regression. For the binomial family, similarly, recall that theta was equal to logit of pi, where pi is the proportion of success, and thus the situation eta equal to logit of pi gives me the regression equation logit of pi is equal to eta is equal to x prime beta, which, as you can see, is the familiar logistic regression. Now, why is this particular link important? Well, often it is the default choice of link in many software packages, for example. This, however, is not the reason exactly why it is important. Now, given a family, how do we choose a link? We have seen some intuitive motivation for this when we discussed the concept of binary choice models. In situations where we do not have any intuition, any prior intuition that is, for example, my application to the Challenger space shuttle data, we can fit many choices of link and see which leads to the best goodness of fit criterion. A third and more mathematical motivation is given by the choice of the canonical link. You will see in subsequent slides that the log likelihood and the score equation simplify. For the case where we have a canonical link, the properties of the asymptotic estimators, they hold in smaller samples, thus giving us some justification for the choice of a canonical link. Now let us derive the maximum likelihood estimators for the generalized linear model. If we ignore the terms in phi, and if we ignore phi for the time being, it turns out that phi is not really important for maximum likelihood estimation because it drops out of the score equations, and in any case we know that for two of the most important discrete families which we consider, there is no additional scale parameter phi. So let us forget phi for now, and we shall revisit it later and see how, having got the maximum likelihood estimator of theta or of beta, we can use it to get a method of moments type estimator of phi if there is indeed a scale parameter. So for now, let us write the likelihood equation as L of theta y equal to y theta minus b of theta divided by a of phi. Now note that this expresses the likelihood as a function of theta. So for example, if this were the binomial likelihood, it would be expressed in terms of the logit of pi. If this were the Poisson likelihood, it would be expressed as a function of the log rate. However, my problem is that I am trying to fit a regression model. If you recall my original slide where I had written eta equal to x prime beta and then related it to y using the equation g of mu equal to eta, the effect of the covariates of y is summarized by the parameters beta. Of course, they are not the usual regression coefficients for linear models, and we shall see how to interpret them in some particular cases. However, this means that our parameter of interest is beta and not theta. So we wish to get the score equation or the likelihood in terms of beta rather than theta, and for this we have to use the familiar chain rule. So let us consider beta j, which is the jth component of beta. Then using the chain rule, we can write del L del beta j equal to del L del theta into del theta del mu into d mu d eta into del eta del beta j. What are each of these components? Let us find out. Del L del theta can be written straightforward as y minus b dash theta over a phi. You will remember from your classes on inference that b dash theta is the mean of the exponential family. So we can write this as y minus mu over a phi. Del theta del mu by same logic turns out to be 1 over b double dash theta. Now you will also remember from your classes in inference that b double dash theta is something called the variance function for the one parameter exponential family. And so we can write del theta del mu equal to 1 over b double dash theta equal to 1 over b mu, which is equal to a of phi into variance of y. The concept of a variance function is something unique for generalized linear models. So for the usual linear model, once we are given that the mean of y is mu, we can specify an independent parameter sigma square which is not related to mu and call it to be the variance of y. This is not so for the binomial distribution, where the moment we have specified the mean to be pi, it turns out that the variance is given by n pi into 1 minus pi. Similarly, for the Poisson case, the moment we know that the mean is given by lambda, we also know that the variance is equal to the mean is equal to lambda. Thus, we have the concept of the variance function, which up to a scale parameter relates the variance of y to the mean of y. So once knowing the mean, it is not possible to specify independent parameters for measuring the variance. So anyway, let us come to the third component. Del eta del beta j is given by xij, as eta is the linear predictor x prime beta. So putting all this together, this means that my score function is given by del L del beta j equal to y minus mu over variance of y into d mu d eta into xij. For canonical links, there are some simplifications. Now recall that for canonical links, eta is equal to theta. So this means that del mu del eta can be written as del mu del theta, which we know is equal to b double dashed y, and which we know further is actually related or equal to the variance of y. So this means that for canonical links, the score function simplifies further and can be given by del L del beta j is equal to y minus mu over variance of y into b double dash theta into xij, and using the fact that b double dash theta is the variance of y for the exponential family, this simplifies further into y minus mu over a phi into xij. So here already you can see that the score equations for canonical links are considerably more simple than for the case where we have a non-canonical link, and this gives you some mathematical justification for preferring the canonical link or making it the default choice when you have no strong reason to favor any particular link. The information matrix is given by minus of expectation del square del beta j del beta k. This is equal to expectation del L del beta j del L del beta k by the properties of one parameter exponential families, which by virtue of what we have already derived turns out to be equal to expectation of y minus mu by variance of y whole square del mu del eta whole square into xij into xik, which is equal to 1 over variance of y, as expectation of y minus mu square is the variance of y, equal to 1 over variance of y into d mu d eta whole square into xij xik. Note that del mu del eta can actually be written as d mu d eta also. For canonical links, we have the result that the observed information is equal to the expected information. Now, the expected information we have seen is given by expectation of del square L del beta j del beta k equal to minus b double dash theta by a phi into xij xik. Now, considering the observed information, this can be written as del square L del beta j del beta k equal to del beta k of del L del theta into del theta del beta j. Using the product rule, this is del L del theta into del square theta del beta j del beta k plus del theta del beta j into del square L del theta square into del theta del beta k. The first term is of course 0. By definition, as del L del theta is equal to 0, and del theta del beta j and del theta del beta k simplify into xij and xik, so that del square L del beta j del beta k is equal to del square L del theta square into xij xik, which can be seen to be equal to the expected variance. To summarize then, for the generalized linear model, the score function is given by del L del beta j equal to y minus mu by variance of y into d mu d eta xij and minus of expectation del square L del beta j del beta k is equal to 1 over variance of y d mu d eta whole square xij xik. The score equation is thus given for one observation by del L del beta j equal to y minus mu by variance of y into d mu d eta xij equal to 0. For the entire likelihood, it simply turns out to be the summation of similar terms from each of the n individuals, and for each of the p beta j's, combining all of this information, the score equation from the entire likelihood turns out to be of the form del L del beta equal to x prime a into y minus mu equal to 0. The information matrix simplifies as minus expectation del square L del beta j del beta k equal to 1 over variance of y d mu d eta whole square xij xik for one single observation, and for the entire data set it can be seen to be expressed as minus of expectation del square L del beta prime equal to x prime wx. The form of a and the form of w are things we will discuss later in the modules on IRLS, but I also leave it to you as an exercise to derive. In the next module, we will consider solution of the score equations. The score equations are not explicitly solved in the sense that it is not possible to bring out beta from any one of the terms, and so we have to use numerical methods. We shall use gradient-based methods, and in particular a well-known algorithm called the Newton-Raphson, or actually we shall use a variant of the Newton-Raphson called Fisher's scoring. We shall see that each iteration of Fisher's scoring turns out to be related to the familiar least squares which we have seen in our preliminary modules on regression, and hence the solution of the score equations can be done using an algorithm called iteratively reweighted least squares. In this module on generalized linear models, we have written out the general likelihood for a generalized linear model. The generalized linear model occurs not necessarily when we have discrete outcomes, but it could also occur for the case where we have continuous outcomes. So in general, the outcomes have to belong to a family of distributions called the one-parameter exponential family, and there may or may not be an optional scale parameter. So we have explicitly written out this family. We have seen that a difference with continuous data is that we have an automatically specified variance function the moment we specify the mean. We have written out the likelihood and the score equations and seen that they do not have any easy explicit solution. In the next module, we will discuss techniques for solving these score equations.